All right, I think it's time to get going. We have a big evening here. The first regular final presentation session of this school here. And so I'm going to send around a clipboard, and the green marks the people who will get credit for attending tonight. So just put your initials either beside the space or in the space. And I will start it back here, and then that can go through the center section too. So make sure nobody gets missed. First. Well, we have the UAV team presenting, and they're divided into two teams, the mechanical team and the electrical and computer engineering team. And so, are you guys ready to go? Or do I need to keep running my mouth for another 30 Well, okay. Well, wait, I don't know any jokes, though. At least whatever jokes I do, I've already used them, so I'm running out of jokes.
And these in the last 4 years?
Probably. But let me think. How about the engineer, the ophthalmologist, and the pastor who went out golfing one day? Have you heard that? Well, they went out golfing, and they were just having a great day. It was kind of like yesterday was, sunny and beautiful, and it was in the spring, and the grass was very bright green. The trees were bright green, and the flowers were brilliant. But about the time they got to the 8th hole, they caught up with a foursome that was really playing slowly. And so they waited a long time to get to play the 8th hole. The team moved on, they played and then they went on to the 9th hole, and they were stuck behind that same foursome again, of course, and they had to wait a long time. And this went on like this for a couple of more holes. So the pastor noticed the head groundskeeper there. So he went over and talked to him because he knows him. He said, who are these guys? And the groundskeeper said, oh, those were firefighters. You remember 2 years ago, our clubhouse burned down? Well, these guys fought valiantly to save the clubhouse. They lost that battle, and they also lost their eyesight. And the pastor said, oh dear, I just want to give a prayer for them right now. And the ophthalmologist said, well, can we get them into my office? I'd like to see if there's something we can do for them. I can do for them. And then people looked at the engineer. He said, well, why can't they just play at night? Does that fit any stereotypes here? Oh well. Big world, huh? Ready now? Okay. UAV team, mechanical folks. The floor is yours.
Have you ever wondered what it's like to soar like a bird? The mission of our aircraft is to mimic the soaring habits of birds. Specifically, we want to copy the ability to utilize what we know as thermals. Thermals are regions of rising air caused by solar ground warming. Thermals will allow a bird to soar without flapping its wings, or an airplane to fly without using its motor. In addition to the 4 mechanical senior engineers, we've greatly appreciated the help we've received from our professional sponsors, Leo Wilson and Michael Allen, who met with us regularly to assess our progress and offer suggestions. Both have been valuable to our process because of their experience, relevant experience in the professional aviation industry. We've also highly appreciated our junior engineers who helped us over the course of the project: Alina Bylard, Martin Shen, Theodore Zirkel, Hector Gonzalez, and Ryan Parrish. To complete our mission, we separated into two teams. One mechanically oriented team to create a light but strong enough vehicle to go and search for these thermals, and a second, more computer and electrically oriented team that will provide, will add the thermal soaring capability to the current autopilot system, which you'll hear from in the second half of tonight. Essentially, one team provides the brains and the other team provides the body. This plane is unique compared to other commercially available RC aircraft gliders because our aircraft is designed with large amounts of cargo room that accommodate the size requirements for our autopilot systems. We also have a motor that allows us to go and search for thermals. We've used several different construction techniques and materials in previously designed aircraft at Walwell University that have helped in making our aircraft both light and strong. There are four major design disciplines that must be considered in the design of an aircraft. There's aerodynamics, structures, propulsion, and stability and controls. Crystal was our aerodynamics engineer. Ashley designed our structures. Zach designed the propulsion, and I designed the stability and controls. Now we'll hear from Crystal about our iterative design process and the aerodynamic design discipline.
When designing in the aerospace industry, it is critical that the four design disciplines communicate and work together throughout the entire process. Each design choice made has a profound impact on every other design discipline. As an example, if I was to change the wing design, this would impact and change the drag, which would change the required propulsion system. Because of this interconnected work, we do our work in phases. So we have our main design, build, test phase that you see here. And because building and testing generally takes a long time and is very expensive, we want to run through a few design and share phases before we get to that building. So we start with a conceptual design that we freeze, and then we move onto our individual design pieces. And then once we've done some of our design, we come back and we collaborate and we come up with a new initial design. And then once we have our new design, we freeze it, and then we go and we work on our individual design pieces, and then we come back and we come up with a new design, and then we freeze it, and then we keep going through this process until we're ready to build. So this is very iterative, as you can see. Our team jumped in with a baseline design that was adapted from competitors. This allowed us to work on our preliminary design. We then came back together to build and fly the aircraft. We gathered data from flight testing, which we will reflect on and analyze to come up with our second design iteration. So I started my aerodynamics design by researching competitors that had similar wingspan and missions as our plane. I chose an area and aspect ratio from the Mystique glider shown on the left. This allowed me to estimate a flight velocity and a Reynolds number so that I could then select the airfoil. An airfoil is the two-dimensional slice of a wing, and the shape of this airfoil will change depending on the flight mission. As you can see from this graphic, airfoils are not specific to aircrafts. They can be used to describe many different kinds of vehicles and even animals. So as you can see, there are some examples here ranging from very low speeds like the Dragonfly all the way up to very high, even supersonic speeds. I chose a few low Reynolds number airfoils, and I used a thin airfoil theory program called Xflyer to see how they would respond to the air. I plotted lift coefficient versus drag coefficient at our appropriate Reynolds numbers to give me graphs like the black one on the right. I chose my 5 favorite airfoils and compiled them into this Excel graph that you see here. We typically fly at a lift coefficient of about 0.6, but during takeoff and landing, our lift coefficient is going to be much higher. I chose the SA7038 airfoil, which is the blue one on the top, because it performed well at our target lift coefficient of 0.6, and it also had a very high maximum lift coefficient of 0.3 for relatively low drag coefficients. I chose the tail airfoil by the same process. So that was all two-dimensional design of the wing. Now we're going to move into the 3D size and layout. Because our mission was to produce a glider, I chose a wing shape that was long and skinny, meaning that it has a high aspect ratio. We can see this in nature, like the albatross. It also has a very high aspect ratio. The eagle on the bottom is an example of a bird that has a lower aspect ratio. High aspect ratio birds or planes are more stable and they produce less drag, meaning that they consume less energy and they can stay in the air longer, which was our main design goal. Because this was a quick design, remember I chose my area and aspect ratio from a competitor, and then I tailored the taper ratio. I ran some MATLAB script that runs finite wing theory, which is a simple way of estimating wing performance. It gave me these two graphs. The first one is lift distribution. This graph is set up with the wing being along the x-axis, center of the wing is at 0, and the tip of the wing is at the tip of the graph. Oh, and it's 1/2 of the wing, just 1/2. The goal was to make this curve as elliptical as possible. If it was a perfect ellipse, the span efficiency factor, which is reported on the bottom line of the graph, would be 1. While I am changing parameters to make this graph elliptical, I'm also working with the other graph, which is the section lift coefficient distribution graph. And this graph tells us how hard each section of the wing is working. And it's set up the same way as the previous graph, with the x-axis being along 1/2 of the wing and the center is at 0. The goal is to make this graph as horizontal as possible. The wing is going to stall where this graph has its maximum, and we wanted this place to be close to the center of the wing as possible. A taper ratio of 0.8 is what gave me these results. So we started our wing construction by making airfoil templates that we could then cut out, so that we could cut out our foam wings using a hot wiring technique. Foam pieces were cut to length, and then the airfoil shape was cut out. A carbon spar was installed at quarter cord, and fiberglass and resin was added to the wing, and then it was placed in a vacuum bag for 24 hours. Ashley is going to expand on this hot wiring technique and vacuum bagging technique in a minute. After it came out of the vacuum bag, the wing, it looked a little rough, and so we had to do some sanding and a couple patch jobs. And after we did that, we cut out our control surfaces, and we installed our servos and our control rods. And then we were pretty much ready to paint. Brendan will expand on some of that control surface stuff later on. Ashley will now discuss the structures and construction of our airplane.
When considering the possible construction materials for a UAV, we have the following main choices. On the left is a balsa structure with a monocoat finish, which is the plastic sheeting that shrinks and adheres to the balsa when it's heated. This method can yield a very lightweight structure, but is very tedious to construct. Also, it's not very forgiving when it comes to doing repairs. On the right is a carbon fiber shell. This is a more expensive material and wasn't a very appealing option for our first iteration. It's also Our material of choice was fiberglass because it's inexpensive and not too difficult to fabricate. It's also more manageable when it comes to doing repairs. The first iteration process, from a structural standpoint, was focused on the manufacturing techniques. And so we simply purchased commercially available carbon rods that we knew would meet our requirements. Beam stress analysis showed that our maximum stress in the carbon rod was well below yield. And for our application, it was sufficient to say that our stress came purely from bending. Our second iteration process is based on refining our design based on stress and deflection data that is collected during our first iteration. My construction focus was the fuselage. I started out the design with this sketch, and from that sketch I created a model of the fuselage in Creo. I then sliced it up at each of these cross sections shown above, and 3D printed templates at each section. The templates are used to turn my design into a reality using foam. They ensure that the foam fuselage is the shape that I initially designed it to be. The Creo model allowed me to find valuable data such as surface area, and using my MATLAB geometry code, I calculated the weight, which is used by the other three disciplines. I cut foam segments to length and then used the templates to shape the foam using hot wire.
Hot wire.
This technique uses current to heat wire that's passed along the surface of the template, and it leaves just the foam behind that is in between these templates. After gluing the foam segments together, I did a fiberglass layup on the exterior. This process involves saturating fiberglass with resin and then laying it on the desired surface. The picture above shows the fuselage in a vacuum bag, which forces as much excess resin out as possible to ensure a lightweight finish. After the fiberglass had set, we dissolved the foam core to make room for all the onboard electrical components, as well as to get rid of unnecessary weight. We then built the center section where the wings are connected to the fuselage, and lastly gave it a coat of university green paint. Coming back to the bending stress that I spoke about at the beginning, those stresses that were calculated were sufficient during steady level flight, but we need to consider gusts and maneuvers, which both create additional stresses on the aircraft. For the sake of time, I'll briefly discuss gust load factors. These are very applicable since the thermals that we are dealing with are simply gusts of hot air that can have velocities up to 5 meters per second. This is represented as the V gust and causes the aircraft to experience a relative velocity and an additional angle of attack. Knowing this angle enables us to calculate the additional coefficient of lift and in turn the additional lift on the aircraft. This increases the applied moment and results in increased stress. From these load factors, we can also determine the factor of safety for our aircraft. Next, we'll hear from Brendan about the stability and control of the aircraft.
In order to begin our iterative design process for the stability and controls, I started by considering different tail configurations. I found that most commonly gliders used a conventional tail configuration or a T-tail configuration. The T-tail positions the horizontal stabilizer out of the wake of the main wing, which increases the efficiency. However, they require more structure to support the added moment forces and can enter deep stalls that are difficult to recover from. Because we wanted the lightest design and that is most simple to manufacture, we selected a conventional tail configuration. Then I researched what length to make the tail moment arm to integrate that into my tail surface design MATLAB code. There are many design details to consider in this project, but because of the importance of longitudinal or pitch stability, I would like to highlight this process. Its three components are horizontal tail sizing, the angle of incidence of the horizontal tail, and the center of gravity location. Conventional configuration aircraft require the center of gravity to be just in front of the center of lift. This is counteracted by a downforce at the tail from its downward angle of attack. My design process began with MATLAB to size the tail based on parameters such as our wingspan and tail moment arm. These areas are critical to ensure static stability. The original design went through several design iterations because of manufacturing issues where the trailing edge of the surface would be melted away by the hot wire technique. Next, I needed to find the angle of incidence that the horizontal tail would be mounted at. To do this, I used Xflyer to plot the lift versus angle of attack of our NACA 10 airfoil. From the required downforce shown on the vertical axis, I selected the angle of the tail to achieve the downforce required to balance the plane. Continuing to use MATLAB, I calculated the aerodynamic neutral point and the center of gravity. From there, I could calculate the moment generated by all the weights and moment arms, giving me the pitch moment force. At the time of design, I found that I expected to have more flexibility in the component placement. However, the as-built aircraft showed that there were certain differences, like extra resin composite in the tail that threw off my moment calculations. We'll consider this in the second design iteration, but for the moment we corrected it with adding extra ballast to the nose. We decided that our tail tail servos should be mounted inside the fuselage in order to reduce drag. Thus, I needed a way to mount our servos. I designed this 3D printed servo mount in SolidWorks by incorporating the three-dimensional shape of the fuselage so it would fit into position well. I made several design iterations to reduce weight. Here is the functional 3D printed part installed on the aircraft. Now Zach will share with you the propulsion discipline and some of his original part designs.
So as a propulsion expert, my job was to get the aircraft to the thermals. How are we going to get the aircraft to the thermals? Well, since we want a lightweight aircraft, the best way to do that is with a small motor. We don't want to do a winch launch aircraft because that would create a much heavier aircraft. On this next slide, you see the propulsion system and its components. Going from left to right, this is kind of the design process I went through. First, we started with the drag created by the aircraft. I got that from aerodynamics. This gave me a rough estimate of how much thrust I'm going to need. I could then determine what propeller I would use. In this case, we decided to use folding props to allow us to reduce drag during our soaring operation. That was our primary objective. So we start with a prop that gives us the proper amount of thrust, and then I would determine which motor would give us the correct RPM and power consumption to supply the proper amount of torque for the prop. Then find an ESC that would match that and a battery that would match that. This is an iterative process, and during the second iteration, I was able to reduce the overall system weight by 110 grams, which is about 8% of the overall aircraft weight. One of the components I needed to make to integrate the system was the motor mount. The fuselage is hollow, it's round, there's nothing to mount to, so we needed some way of having a solid mount for the motor. So I designed a 3D part to put the motor on. The problem was that since we dissolved the foam out of the fuselage during the building process, our inside diameter was actually smaller than we expected, and we also had a slightly different cut on the nose length. So this meant that I had to do this in 2 iterations to get a proper part. In the second, one of the second iterations, I was able to change the shape of the part to reduce, to bring it closer to the nose to reduce weight. Once I had this part, I then could work on the folding prop. To integrate the folding prop, I needed to create a prop adapter. Most props use a standard hub, but they are fixed. They don't have a special hub that folds back. To incorporate this special hub, I needed to create an adapter that had a collet on it. So I went back and looked at this part, figured out what design characteristics from it I could take, and then which ones I needed to change. Then I created a 3D model of this and went to the lathe and started to machine the part. After this, I was able to take 3D coordinates or 2D coordinates and place the part on the mill and properly drill each hole in the proper location so that it would correctly match the motor. Next, I would like to talk to you guys about the prop testing. The prop testing, prop analysis can be very complicated, so one of the best ways to actually get a good estimate of what thrust you're going to get is to actually go out and test it. So what we did is I performed a number of static thrust tests on our propulsion thrust stand. This gave me the efficiency of the prop, the maximum thrust that the prop can give me, and how linear the thrust to power was. Since the thrust was linear, I was able to make fairly linear. I was able to make a fairly linear fit with that and send that to my model to determine what my flight time was in MATLAB. And then that way I could make the best decision on what battery to select. Next, but the problem with this is that it is static thrust, but our aircraft's actually moving. So to do final testing, we need to start our flight testing. This would give us the actual motor's prop performance during movement. In our flight testing, the first thing we need to do is create a checklist before flight. What do we need to know? What do we need to before we fly? Are all of our batteries charged? Is there any structural damage from past flights? Do our control surfaces actuate properly? Just as we would in a real aircraft, to protect our investment and to have the smoothest operation. Each member created a plan for their set of flights they wanted me as the pilot to perform. So for example, me as the propulsion expert, I was interested in the flight time, how was my battery properly sized, and how well does the aircraft climb? Did I have enough power to get the aircraft up to the thermals? Brennan would be interested in how stable is the aircraft? Did we get the control we wanted? Could we maneuver around the thermals the way we are intended? Aerodynamics wants to know how the wing performed. Did it glide properly? Did we get proper soaring with the aircraft? Structures wants to know, well, how much force is the aircraft taking? What's the maximum turn we can perform on the aircraft? Is it going to be strong enough? Are we going to have any structural issues? Next, I'll show you guys a video from some of our test flying. This is from our 5th test flight, but you should have seen our first one. We ended up hitting the back of Brendan's head with the tail, and we didn't actually include a safety factor for that, so we did have to make some repairs. But you can see we've repaired it. The fiberglass is very easy to repair, so we were able to do that. I was very happy with the control of the aircraft, the stability of the aircraft, and also how its glide ratio is also very good. All characteristics we really were hoping to get in our aircraft for thermal soaring. Next, Ashley will talk to you guys about future works.
In parallel to our construction work, our team has been working on a computational model of the aircraft in MATLAB. Our code simulates the physics of each discipline and then pulls all that data together to predict the aircraft performance. To improve accuracy of our model, we augmented it with our flight test data. So, our final steps are 1. To compile flight test results, 2. To tune out our code, and 3. To use our MATLAB design tool to virtually flight test other configurations to select an improved design. Do you have any questions?
Yes.
So, Brennan, you mentioned that you had to stick some ballast in the nose with balance. Is that, I mean, could you just trim the tail instead? I mean, that doesn't fix the problem. That's beyond the next stage. But can you trim the tail with that, or trim the elevator?
You can achieve some stability out of that. However, the primary purpose of having center of gravity in front of the center of lift is to, if your aircraft encounters some gusts or something that cause your airplane, for example, to have a greater angle of attack, the center of lift will counteract that center of gravity force and bring the nose back down. Conversely, if the plane tipped down to the tail would bring the nose back up.
Thanks. Thanks. One more. No one else does.
Riley has a question.
Those wings have the ends of them tipped up. If they were not tipped up, what would be your performance penalty?
Are you asking me or Brendan? Because it could be either of us. They're tipped up because of a stability question. So we wouldn't be as stable if they weren't. That's why they're there. So that's kind of, I don't know. Brendan, do you want to add anything?
Aerodynamically, there would be no penalty necessarily aerodynamically, but they create passive roll stability in the aircraft. I'd only necessarily have a qualitative measure to say it wouldn't be as roll stable.
And what determined the angle?
From our iteration process, we selected an angle based on looking at our competition and the likely be more in-depth analysis during our second design iteration.
Follow-up question. I saw you pull out this large piece of paper earlier.
Yes.
and said that somehow came about, and as a result of however it came about, then actually made some CAD 3D printed things in order to make it. But I don't recall hearing how that thing came about. That design you're holding in your hands, how did you design it?
Well, it was also based on competitors.
Oh,
And also,
when you say competitors, I saw a picture of a competitor. But how do you deduce that from a photograph?
well, I didn't exactly trace it from a photograph. Everyone knows how a fuselage looks, and so I kind of just used that idea to draw out a side view of the fuselage, but taking into account the size of our onboard computer. And so the diameter of the fuselage was based on what size we need to fit the onboard components.
What performance penalty would there be if that fuselage was square instead of round?
I don't know. That's a drag question. There would be more drag is the answer.
I don't recall seeing an analysis of the fuselage with respect to aerodynamic ability. I saw analysis of wings. Did you analyze that carefully designed fuselage?
No, that is part of my future work that he talked about our MATLAB code. That is a piece in my MATLAB code. But not for this airplane, I did not.
In my geometry code, I also take into account the surface that the wind would see, and we divide that, we multiply it by about 0.8 to account for the taper on the fuselage.
I think Greg had a question being Professor Smith.
Okay. Did you make account for the drag of the proper make?
No. No, the prop folds back, so when we are gliding, it won't produce. No. It's going to be negligible when we're gliding because the prop folds back.
Okay.
Yeah. You have another question?
How do you measure the airspeed so that you can know that you're going forward or going back, or how do you?
Yeah, that was part of our flight testing. Yeah, that little thing that Ashley just touched.
This is a little mount for a pitot meter, which takes the differential between two air pressures and uses that to calculate the airspeed.
Okay.
Yeah, I got a tough one for you. You compared the albatross and the eagle,
Yes.
and you chose an aspect ratio based on the albatross.
Yes.
But who uses thermals more, an albatross or an eagle? Albatross? Do they use thermals, or do they use, winds aloft over the ocean?
Yeah.
Because eagles do a lot of soaring in thermals.
They do. Yes. But albatross can stay up over the ocean for a really, really long time.
Yeah.
It's using the same type of thing.
I'm going to say albatross use a different kind of soaring technique. That's more, I think it's called dynamic soaring. And so it requires there to be a wind gradient so that close to the water there's less speed and velocity increases, and so they can kind of do this.
Yeah, but you guys are doing thermal.
Correct.
So would an eagle be better at thermals than an albatross? In which case, don't you want your plane to look more like an eagle's?
An eagle is designed more for acrobatic type flight, whereas an albatross is more for kind of more steady level type flight. So we would go after a
Lower aspect ratios are better for maneuverability.
And you could also say that an eagle needs to thermal soar more because they are less efficient, so that it takes more oxygen to
Improving on me.
My question was if you guys did any basic calculations to actually tell which aspect ratio is going to be better.
Yeah, it's in, I did some, in my taper ratio code, aspect ratio is there, and so I could play around with it a little bit. And I actually did change it just a little bit from the competitors that I mentioned. It had to be scaled in the first place because the wingspan wasn't exactly the same. But then I did change it a little bit, but not, it wasn't significant now change.
Yeah. Two quick ones. One, what was your stall speed?
It was about 2.5 meters per second.
Okay. Second one, why is there a picture of Frisbee on the slide?
Oh, I don't know, I should
Based on the final presentation last year, Professor Riley brought up why we don't just build a frisbee.
This is our prototype from our second design year.
Yeah, there's a lot of competition you can base that on.
Why didn't you get an aerobie instead of a frisbee? Aerobie's going to go further.
Propulsion question?
I do have a question. How is it that you were able to reduce the weight of the motor prop combo so much in the first?
Yeah, so what happens in our design process is we start with a baseline design, but if I was able to get the design light enough the first time that we can say, oh, well, our drag is reduced. So that means that they can give me even lower drag, or a lower, since the weight is reduced, I can get a lower drag estimate and then make the system lighter. So the more you optimize it, the more you can do that again. So for all the weight I save, I can save even more weight, generally speaking. That's why it's an iterative process.
So you did save some weight, but is it actually going to save a lot of energy over having, well, let me rephrase that. Is it going to be significantly better in some way to have a smaller motor and the less weight? Because it seems like you could have a higher power output from a larger motor.
Yeah, you would have a higher power output, but the thing is then our battery life would be much shorter because our efficiency wouldn't necessarily be as good. We also would need a bigger battery, so generally the weight gets gets on the battery is the thing that's going to get bigger. Even though we could have a larger motor, we generally don't want to have to increase our battery size.
Getting set up. Has everybody had a chance to mark this? I noticed that there are about 6 people who said they were going to be here tonight that didn't sign in. Okay. Not here.
So you just started the mechanical team, and now we're the brains of the operation. We're the machine learning for thermal soaring team. So basically what we want to do is we want to take that eagle or the albatross, and we want to put the brains of an R2-D2 basically in it. We want to do what it does for the thermals, but autonomously. So our team consisted of us 3 seniors, and we also had some underclassmen also helping us. We had Robert Berglund and Jeremy Gaines. They're sitting right there, so thank you guys. And then also Professor Sterling was our advisor. So what do we want to do? We want to do the same thing that we were talking about earlier. We want to be able to soar in thermals. However, we want to take Zach out of the picture. We want to basically replace Zach, and so you don't have to have someone manually trying to fly through all these thermals. So we want to have the glider come down, send us a lot of data. We process that data, figure out where the thermals actually are, and send commands back to the autopilot to tell it where to go. So my goal in this project was to kind of provide us with a base implementation we could compare against. So I used existing research. One of our sponsors, Michael Allen, actually did significant research on this with NASA, and we implemented a basic algorithm to compare to. The first step of that was to make an energy equation, which thankfully was already well researched. And this basically gives us an idea of what the energy is like in the air. Essentially, we're flying, gathering our data, and we want to know as much as possible, and we want to process that to know when we suddenly get some lift. So when you graph this energy equation as we're flying along in simulation, you can see that over here goes along, and then suddenly I hit a thermal. Boom, it spikes. And when that spike comes, that differential, that's when I latch onto the thermal. And my simple little algorithm says, hey, there's a spike, great, I'm in a thermal, I'm going to latch on and ride this thing until it goes away. And then when it goes away, it goes on with its mission. So what does that look like? Well, this is kind of the simulator view, my own personal view. This is my left screen. I got a view of the plane, so I can have a nice visual of what's going on. I have all this complicated stuff. This is all the stuff that I'm setting up in the simulator. So this is where I create the thermal. This is where I set up my plane. I can toss it up to 1,000 meters with a little click of a button. It's great. We can't do that in real life. And then I have some C++ code behind it. And then this is my other view. This is the Piccolo simulator that I'm using here. And here I have my plane set up. I'm going towards the destination. And in the middle, I've hidden a thermal somewhere. And basically, I'm trying to see if I can find that thermal. Thankfully, right in the middle, I found it. And I set a waypoint there, and then you can see my plane has started orbiting that thermal. And then if you were watching the simulation, you could see that the altitude was slowly rising as I followed that perfect thermal. So what next? This sounds great, and it does work, in simulation at least. It's been working fine. We're working on the rest. But the disadvantage of this approach, one is it's very simple soaring logic. Basically, I just latch if I'm getting lift. I don't really have this isn't great, I'm going to move on to another thermal. I'm just, I'm getting lift, sweet, I'm just going to stay here until it goes away. And then we don't really know what the thermal truly looks like. Currently, I'm just using a very basic batching method, similar to Alan's centroid method, where basically he's trying to estimate where the center of the thermal is at all points. But we don't really know what the thermal looks like, and that has a bunch of different issues with it. So that's where Garrett and David come in. So enter Garrett and David, and they'll be talking about some more improvements we can make to this algorithm.
So my part of this project was trying to improve the detection of a thermal, the thermal identification, trying to make the most of the limited data we have access to. So here you see a simple thermal model. Our plane is flying along its flight path, and it's collecting data, such as vertical velocity. And this data is shown here represented by the points. And that is all the information we have access to. And from that limited information, we want to get an idea of what the thermal looks like so we can go toward the region with the highest vertical velocity and stay within that upward vertical velocity so that we can stay up in the air longer. I looked at a couple different approaches that we could use to take this data and figure out what the thermal looks like. The first is Bayesian parameter estimation. This model on the left has 3 different parameters: the center location, the maximum upward velocity at that center location, and then this fall off. So how quickly is it going from high max vertical velocity to 0 vertical velocity? If we take the data points on that plot and then run it through Bayesian parameter estimation, and then take the most likely parameter estimates and run that back through our model, we get something that looks like this model in the center. So it's similar to the actual thermal, but it is different because we only have the information of these points shown on the left. But this requires that we have a model. If we don't have a model, we could try something like Gaussian process regression, which is a model-less approach. Basically, it takes the same data points that we ran through Bayesian parameter estimation, but it interpolates between them and extrapolates beyond them to get make predictions about the vertical velocity everywhere, including the points we put in, but also everywhere else. But this is an unrealistic thermal model. Because of conservation of mass, if the air goes up, it got to go somewhere. So it goes up, and then it comes down around the upward vertical velocity. So you get upward vertical velocity surrounded by downward vertical velocity. So let's try to compare these two different methods on simulation data using this more realistic model. On the left, you can see Gaussian process regression, and on the right, Bayesian parameter estimation. The top is 45 seconds entering the thermal, and the bottom is 45 seconds of data exiting the thermal. And you'll notice that the left figures of Gaussian process regression correctly found the downward velocity, then the upward velocity, and then the downward velocity. The Bayesian parameter estimation did not. And that makes sense because it's using an incorrect model, and it's not a good enough model. So because of this better prediction based on this data, and also because Gaussian process regression is so much faster, I decided to initially start off by just using Gaussian process regression. But now we need to run this thing in real time in the simulator. So the simulator shown here on the left, I grab data from that in my Python code. I do a bunch of processing with the Gaussian process regression, and then I come up with commands to send back to the autopilot where it'll then tell the plane what to do. And here's the result. Similar to Travis's, but using my attempted improvement instead of the centroid method. On the right, you can see a basic flight plan. The plane will take off, fly this rectangular flight plan to gain altitude till it gets to 200 meters above the ground, where it cuts the engine and starts gliding. It will then start recording data that is continuously running through Gaussian process regression. It is making predictions about what the vertical velocity looks like within about 20 meters of the airplane. And it will label the highest point, circled in blue, and if that highest point is greater than 0.5 meters per second upward with about an 85% confidence interval, it will say, we have found a thermal, and tell the autopilot to go circle that point with a 5-meter radius. And you can see here, it has actually been successful. It found a thermal, and shown by these red dots on the bottom left, it has orbited this twice now. So in comparison with the centroid method, this is an improvement in that we don't just have one point, the center point. We have an idea of what the entire thermal looks like. So now, David will be sharing how he looked at improving another aspect of the thermal soaring.
Okay, so my part was all about developing a strategy for the UAV to get as much energy as it can from the thermal. And we already kind of had a strategy to do that, like Travis talked about, using the energy equation, but I want to do that using machine learning. And there are two reasons for that. Number one, I thought machine learning is awesome, and I wanted to use it. And number two, machine learning has the capability to sort of adapt to the situation, and it's not fixed to a rigid model or rigid assumptions about what the thermal looks like. So it actually could give us a lot better performance. So I mentioned I want to develop a strategy. The technical term for that is a policy. And a policy is something that if you're in some place, it says, and you should do this. So given a state, it chooses an action. So to illustrate this, I have a maze here. And if you're in the bottom rightmost square, it says you should go up. And this policy eventually guides you to those red circles. So the policy tells you what to do based on where you are. So I'm trying to develop a policy that if the UAV follows it, it will maximize the amount of energy that it gets from a thermal. And I want to develop this policy using machine learning. So there's a whole lot of things in machine learning. It's a massive field. So I decided to get acquainted with it. I took an online class, read a book. And once I had a vague idea of what was going on, I started looking for software that would allow me to implement these ideas. So I started out doing some stuff in MATLAB and toyed with TensorFlow for a while. I eventually settled on a Python library, which is open source and called PyBrain. So PyBrain is great, but it's not really documented that well. And I didn't actually know Python at the start of this project. So there was a lot of me messing around with stuff. So you can see here I'm trying out some classification. On the right, I'm trying out some regression stuff. I also did a lot of digging around the source code and seeing what object inherits from what and how everything all really stitches together. Once I had some idea of how that worked, then I was able to make a very, very, very basic solution. So you see this blue line is straight and it goes down. It is a very happy thing. Basically means I told it that there's a lot of reward, on the left and not very much a long ways away from the thermal.
And it learned, well, I should go towards the reward, not away. Which you'd be surprised how hard it is to get to do that. Anyways, so that was good. But I realized that this method is not really all that practical. Because the way I was storing the policy, what to do based on where you are, was, in this state I should do such and such. In this state I should do such and such. I had this massive table. And I realized once I scale this up to something more realistic, the table is going to get absolutely horribly large. And it's going to get completely impractical to get good estimates of what we should do in every single state. So I use something called a neural network, which this is what a neural network looks like. The basic idea is, if in this state we do such and such, and in this state we want to do such and such, then the neural network can kind of like guess in between what would be a good idea to do. So we don't have to store as much stuff. So unfortunately, it didn't really seem to work. Decided let's oscillate towards and away from the reward. And let's run away from the reward. Like we're scared. So many weeks of debugging ensued. I still think this method called neural fitted Qlearning has like a lot of promise. And there's a number of problems with it right now, but I realized gradually that a really key problem with this is that it's not incorporating the model information that we have. Like Garrett's been developing this wonderful model of what the world looks like, and it's just not using this information here. So I switched to a method which is called dynamic programming, and it is still developing a policy, but now it's using our model information. And this allows it to converge a lot faster. So I got this idea from this book, Reinforcement Learning and Dynamic Programming using Function Approximators. So, and a key component of this new method is not only now do we have a policy network which tells us what to do when, we also have a value network which tells us how good it is to be here. And the two interrelate. If I think it's really bad to be here and amazing to be over there, then I'll make a policy that takes me over there. So they update each other in a sort of a tug of war, and hopefully it eventually stabilizes and converges to something wonderful. And I don't know if this is really wonderful, but it does converge to this right now. So this is the output of the value network, and this is the output of the policy network. And the top thing, the value network, you can see it sort of peaks in the middle, which means it thinks there's the most value from being in the middle, which makes sense. That's where the thermal is strongest in the model I'm using here. And this policy says, the blue line says, let's go towards the thermal, and once we get to where it's strong, then the red line takes over. It says, then we should start orbiting. So this is like pseudo-realistic behavior. So I was happy for that to finally come out. There's a lot of work to do here still, and Travis is going to talk about some of that.
Yeah, so now we have three basic components. We have a basic implementation, we have some great thermal identification methods and modeling, and we also have kind of a policy that's starting to take place of what to actually do in these thermal situations. So now we want to kind of combine all these components together. We have me, I'm kind of looking at what the autopilot is seeing, looking at what the plane is seeing, gathering that data, processing it, and then what I want to do is I want to hand that data off to Garrett. And then he can make a model of what the thermal is currently looking like. He can then pass that model over to David, who figures out what we should do next, and then I can tell the autopilot exactly what to do next. So all this should be running in real time as the plane is flying. And that's just something we're going to be trying to work together to get this done before the end of the year. Any questions?
Is the whole process happening in the airplane at the same time, like computation, or is it sending data to like a computer on the ground?
Good question. Yeah, it's sending data currently right now to our ground station on the ground. It would be a nice thing to be able to get this all on board, but that would require probably even more cargo space and a bunch of other things that we didn't want to mess with. So, future projects.
So you can currently hack the signal and tell the plane to do other things.
If you wanted to, I'm sure you could probably do that, yes.
We have a wonderful thing here called the National Weather Service. Are you able to use any of their data to help improve your guessing besides having this do it just on its own?
That's really interesting. I don't know if I'd really thought of that per se. One of the reasons is because thermals are constantly in flux. So, for example, you may have certain areas that are better for thermals, but the National Weather Service, unless they have unless they basically fly through that area all the time, they're not going to have really good data for us, especially at the heights that we're actually flying at. In terms of finding good spots to practice for thermals, that might be a very good idea. Great.
I had a question, sorry.
Dr.
Wondering if we could run back to one of Garrett's slides. Quite a lot of data in those pictures, and you hit the highlights, but I'm wondering if you could come back and share some of the details. Looking in particular at some of those red points, and wondering what those represent, where those come from.
So the idea here is these are all probabilistic approaches. So it's coming up with a probability distribution over where the center of thermal may be. So it's not saying the thermal is at this point here, but it's around that point most likely. And so the greater density of the red is the more likely, most likely location based on sampling algorithms to get, like the Gaussian process regression is a Gaussian distribution, but the Bayesian parameter estimation, I'm approximating an arbitrary probability distribution, which then those red points are individual samples from that distribution.
Is there a certain height at which it would be ideal for thermal soaring, or is it you're just saying that arbitrarily, like I think you mentioned before, 200 meters was a good enough height where you could perform that?
So that 200 meters was just what appeared to work in the simulator. I think Campbell said something about 600 feet would be a good starting point, but I haven't looked into that whole stuff.
And is that like kind of the height that you would be shooting for and telling the plane to stay at that level, or
it's kind of it goes up to somewhere around there, and then it will fly until it hits a thermal, and then it'll go above that as it's finding thermals.
Most of the concerns with height are to make sure it doesn't go out of our view. Currently in this project, with the simulator, we can instantly teleport it around until it seems good. Like I was running at like 1,000 meters in my simulator, so it depends on where you put the thermal, really. But,
Would you be able to use temperature gradient information or?
yeah, so that's something we originally looked into a lot because it's like thermal, right? You should be able to like use thermal IR to like sense it or something. The problem is a lot of for example, you have a thermal camera. That uses like radiation from like a heated body or something like that and all that stuff. And trying to find accurate information from the air is really difficult. So there are some very experimental, I believe, procedures that make use of other types of data that are trying to look and see like, there might be a thermal in the sensor with this specialized camera or whatever, but we haven't found it to be that useful. Temperature sensor plane, we could technically use that. However, if you're in a thermal enough to get a temperature difference, usually you'll notice the lift much clearer. And technically speaking, if someone started blowing the hot air gunners, I don't know, like you could have a lot of weird manipulations with heat and cold, etc. Plus, the colder downdrafts, sometimes you actually want to go towards that because the downdraft might need an updraft on the other side. So.
A question for David. One of the last methods that you talked about was dynamic programming. And you mentioned that with dynamic programming, there's a policy network and a value network, and they had to interact with each other. Can you tell us a little bit more about that interaction, how they work together?
Yeah. Okay. Yeah, I sort of was rushing through it a bit. But the value network keeps track of how good it is to be in different states. So like I was saying, if it's bad to be here and good to be there, then it really seems like I should be updating my policies so that I go there. So this arrow drawn from the value network to the policy network means that we're making the policy network greedy with respect to the value network. So that means everywhere we're going to make our policy such that it grabs the most reward it can. Then the arrow coming back is maybe a little trickier to understand. Basically, if you change how you're interacting with the thermal, maybe you're heading towards the source of reward, and before you were just heading off into a place where there was no reward at all, then that's going to change the value of where you are right now. So based on smarter choices, that can really change the value of certain places. So that's how the arrow comes back. And then it just keeps doing that back and forth.
How are you guys planning for if there's legal issues with flying certain airspace or being too far away from your signal or manual override kind of stuff?
Yeah, so one of the things about at least the Piccolo autopilot, I don't know if I would, and Pixlock as well, is that it kind of has this auto switch off that will switch into manual control after certain parameters, boundaries, and also at any time you can flip the switch and go back into manual control. So in terms of it going out of control, et cetera, with that, on the other side of things, just being legally able to fly, I believe Zach has more information about that.
Yeah, I have a license basically with the FAA now, pretty much all model people in model aviation need that. Since all of our testing is pretty much within the side of the aircraft, even if it's not in manual flight, as long as it's within, we need to be able to see the aircraft physically. So at this point, we're not really worried about going cross country or something, so that's not a concern at this point.
My question's for David. Did you find that as you were training the computer, it ever came up with a good strategy that you had never thought of before that?
Well, it was working in such a simplified world that it was really hard for it to do that. It did manage once, though, that I remember just at the moment. This here, this is graphing how far away we are from the center of the thermal. And once I started keeping track of which direction the airplane was facing, taking into account the real airplane can't really oscillate, it's kind of impractical. I hadn't really realized that if it was right close to the thermal and decided to keep going forwards, all of a sudden now it's going away from the thermal. So in effect, without turning around, it has reversed its direction. So it managed to exploit that to do some weird stuff that it hadn't expected. But yeah, that can be a lot. But yeah.
What's the maximum distance your plane can fly from your control unit?
We have not, the current setup is not quite ideal with the antennas we have, so we'll fix that before and check that before flying it. At the current setup, if it loses control, it'll just revert to manual, and Zach will have to bring it back.
Basically, our ground station antenna is a lot shorter range than the manual control antenna, so it's kind of what we're relying on. Brendan, you want to add to that?
I was just going to ask why would the manual antenna go farther than the computer?
I don't know if we know per se. Most of what we're going to be focused on has been simulation, and it's kind of just the default one they give you. I think currently we're using our wireless router antenna. So we couldn't find one that they used last year. So we found something that works, and we've been making very, very short flights currently. So that's something we'll be seeing.
Actually asked this exact question to them, and how far can we fly it? And they're like, it's far enough. So this kind of test, I guess, is far enough.
So what type of latency would you be expecting as it's sending information, and how would you account for that as it evaluates your data and then sends it back to the aircraft?
Well, I have some of an answer. 720 hertz, right? Is it Piccolo? Okay. Well, on the Piccolo, this is something again that's kind of a little bit we're going to get more into the stages of. On the Piccolo, we're currently sampling at 20 hertz, and we can pretty much process that data in time because I'm running it on my computer, which is pretty nice. And running on a laptop, we have a laptop. At least I have a laptop in mind that should work pretty well. But that is actually definitely an issue. I don't know exactly what the Pixhawk's latency is, but if we wanted to have, for example, if we were going to originally use Bayesian parameter estimation, and Garrett was getting really worried because it was he put in some values and it'd take 4 minutes to come out with something, which is kind of scary. Currently, Gaussian process regression is being a lot faster. He's able to get pretty much real-time results. So we're not, we're pretty happy with that. But if we wanted to ever put it on the plane itself, then we might have serious issues.
Something I should add to that. I'm really unsure right now how much delay is going to be involved in my part. It could be that I can do a ton of training and simulation, and then when it's online, it just basically consults trained results. Or it could be that the simulation is just so different from the real world that it has to do a lot of learning online, in which case that could be a considerable delay. Somewhat.
Now, does Dr. Baltrush have a question here?
What kind of data are you sampling? Are you looking at accelerations?
Yeah, so I can talk about that. To go back to the very beginning. There we go. Okay, so this is the energy equation we're currently looking at. This is something that Edwards, a researcher that kind of took after Michael Allen's research, looked at. And I have a bunch of different things in this graph. So one of the things that we're kind of primarily focused on is kind of the vertical velocity. velocity down. So what kind of velocity are we hitting basically in the negative direction? I have a negative sign there, which means like I'm trying to look at the velocity that's shooting me upward. So if I have high velocity that's shooting me upward, that's kind of the primary indicator. That's actually the only thing we used for some of our initial tests. Then I have a little bit more complicated things. I have the airspeed that we're accounting for here, because there's some fluctuations in airspeed that can indicate the thermal. I have to use the differential and divide by gravity. I have a sink polar rate, which is kind of the sink polar. I use some stuff that Edwards had already calculated for that, which is kind of how much the aircraft sinks in the environment and how much that affects the energy that you'll be reading. I also have the acceleration in the z direction. If we're going to get kind of some acceleration shooting you down or upwards when you enter a thermal. Notice it's a negative sign, so I'm looking for whenever I'm accelerating upwards. And then I also have to account for the prop. Since we're actually a powered glider, ideally we won't have to worry about this, but I want to be able to sense thermals even when I have the prop going. So I try and account for the prop, and I get dynamic data for the actual current power of the prop. Then I also have things like the prop diameter and stuff like that, and try and keep all that data under control. So that's kind of some of the things that we're currently sampling.
Okay. Well, thank you, gentlemen. Our two teams this evening have set a kind of a high bar. All right. Well, next Tuesday we have our next session.